Okay, I think we are live now.
Okay.
So Shivdas, maybe we can begin now.
Okay, great. All right.
Okay.
Morning, good afternoon, or good evening, everyone, depending on where you are. So today we have a special speaker, Professor Ian Petersen, who was my PhD advisor. So Ian R. Petersen was born in Victoria, Australia. He received a PhD in electrical engineering in 1984 from the University of Rochester. From 1983 to 1985, he was a postdoctoral fellow at Australian National University. From 2017, he has been a professor at Australian National University in the School of Engineering. He was the interim director of the School of Engineering at the Australian National University from 2018 to 2019. From 1985 until 2016, he was with UNSW Canberra, where he was a scientific professor and an Australian Research Council Laureate Fellow in the School of Engineering and Information Technology. He has previously been ARC Executive Director for Mathematics, Information and Communications, Acting Deputy Vice Chancellor Research for UNSW, and an Australian Federation Fellow. He has served as an Associate Editor for the IEEE Transactions on Automatic Control, Systems and Control Letters, Automatica, IEEE Transactions on Control Systems Technology, and SIAM Journal on Control and Optimization. Currently, he is an editor for Automatica. He is a Fellow of IFAC, IEEE, and the Australian Academy of Science. His main research interests are in robust control theory, quantum control theory, and stochastic control theory. So it's our pleasure to have you, Ian, here. Over to you.
Okay, thanks very much, Shivdas. So what I want to talk about today is a survey of quantum control engineering, which is really just a discussion of some of the topics that I've looked at when in my research in this general area of quantum control, which is quite a broad area. And I've looked at some specific aspects with my collaborators and students. And so I'll be concentrating on those aspects. Here we go. So first of all, I guess it's well known to many people that quantum technology and quantum information have become important areas of research. And they've provided some motivation for an area of research called quantum control systems. So my background is in control theory and control systems, and in particular in robust control systems, but I became interested in this area of quantum control systems. So one aspect of quantum technology and quantum information is in quantum optics, and that was one of the ways that I got into this quantum control area. And there's a picture here of a lab which Professor Eleanor Huntington had back at UNSW. And so a typical experiment like that involves things like lasers, optical cavities, and mirrors and things like that. So I haven't been really concerned so much with the experiments, but more concerned with the underlying theory. So a recent Nobel Prize in physics was also in this area of quantum control. This was the prize by Hiroshi and Wineland for, quote, groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. And really what they were doing was an example of quantum control, even though it doesn't actually mention the word control there. So there's been in the physics area lots of advances in experimental physics and in particular in the quantum technologies, but the stage is gradually being reached where quantum technology is possibly moving out of the domain of being purely physics, and there's a lot of engineering that needs to happen there as well. And quantum control theory is hopefully going to play an important role in this aspect of quantum technology. So quantum physics places fundamental limits on how accurately we can estimate and control things. And so these are going to be a fundamental issue in quantum technology, and combining quantum physics with control theory is a way of looking at those limits, what they mean, and how close we can get to those limits. So in particular, we need new kinds of control theory which deal with systems which are described by the laws of quantum mechanics rather than classical physics. So most of existing control theory has been predicated on models of physical systems which essentially relate to classical physics, but now things need to change slightly because of the unique properties of systems that are described by the laws of quantum physics. So there's lots of potential applications of these ideas of quantum control in things like quantum sensing, quantum communications, quantum teleportation, quantum error correction, quantum computing, and gravity wave detection. So not all of these have been realized yet, of course, but I think quantum control theory can have something to say in many of these areas. So the basic idea of most control theory is that we start with models and then we apply techniques like optimization to try and synthesize control systems. So in quantum control, we can look at models which take the form of the equations that arise in quantum physics. And these sort of equations are things like Schrodinger's equations, master equations arising in quantum physics, and also an approach that I look at quite often, which is quantum stochastic differential equations. So these kind of models, in particular the ones such as Schrodinger equations or master equations, are often used in what's called open loop control, where we don't have a feedback loop, but we just apply a particular control strategy as a function of time. And in particular, when applying these to what are called finite level quantum systems. So where the underlying Hilbert space in our quantum system is a finite dimensional Hilbert space. So for example, in problems such as in NMR or in quantum chemistry, then this kind of open loop control where we design pulse shapes, for example, RF pulse shapes in NMR or laser pulse shapes in the case of quantum chemistry, is an important application of quantum control, but it's open loop quantum control. So other models such as these QSDEs, quantum stochastic differential equations, are more often used when we're looking at feedback control and also where the underlying systems are continuous variable systems. So for example, optical cavities, microwave cavities, they are continuous variable systems rather than finite level systems. So these stochastic QSDE models can be used to describe optical systems such as optical cavities, optical amplifiers, and optical squeezers. And also in the microwave domain, things like superconducting microwave circuits. So continuing on this idea of using feedback in quantum control, another idea which has emerged recently or over the last few years is the so-called coherent quantum feedback control. So here we've got feedback in our control system, in our quantum control system, but in control system language, we've got a system that we're trying to control, which is a quantum system, and then we apply feedback to that, also using a quantum system. So both what's the plant, the system we're trying to control, and the controller are quantum systems. So in this kind of very schematic looking diagram, we might think of our quantum plant as something like an atom, maybe that's a finite level quantum system, and our quantum controller is maybe something like an optical cavity. So that's this notion of coherent quantum feedback control. So as I said, the basis of most control theory is starting with a model. And in quantum mechanics, we've got our two main pictures, the Schrodinger picture and the Heisenberg picture. And both of these are commonly used in quantum control. So let's start with the Schrodinger picture, which the typical case is the Schrodinger equation for closed quantum systems. So if we've got a closed quantum system, it doesn't interact with the environment. And so the quantum state of that system will evolve according to the Schrodinger equation, which depends on the free Hamiltonian of the system. This is a Hermitian operator on the underlying Hilbert space. And so this might be quite a useful model to use for finite level quantum systems, because if we've got a finite dimensional Hilbert space, then the state is a finite dimensional vector, and it evolves according to an equation like this. So, this kind of model is very useful for finite level or finite dimensional quantum systems, which is an appropriate approximation for many practical situations. So, and in particular, often the control of these systems is via open loop control. So, for example, if the Hamiltonian in our closed quantum system, in fact, depended on certain functions, which are the control functions, which then form part of the Hamiltonian. So the Hamiltonian would have a fixed part, the free Hamiltonian, and a time varying part, where the time variation comes from our control U, then our overall Hamiltonian is varying with time, and the time variation comes from how we adjust the trajectory of this control input U. Then we get, say, a corresponding Schrodinger equation, where the Hamiltonian now is a function of time. And a typical open loop control problem for this situation would be that we want to find some time horizon, capital T, such that we can find some control laws, which is like the functions of time, the UK is a function of time, which steers the initial state of the system. So that's some vector where the state of the system is at time 0, for example, to a predefined final state where we want to get to after this time, capital T. So they were probably the first kind of quantum control problems we looked at. And then within this open loop framework for finite level quantum systems, it was also realized that often it was more practical to deal with mixed states rather than pure quantum states. And in this case, we have to modify the Schrodinger equation to a master equation. So we're still dealing with a closed quantum system, but now dealing with mixed states. And so the state of the quantum system then becomes the quantum state density operator rho, which evolves according to a master equation like this. So we still were dealing with finite dimensional systems. So rho would actually be a matrix. The Hamiltonian would also be a matrix, and we'd get this evolution. And similarly to the above, we can assume that we can suppose that the Hamiltonian actually depends on some control input in a time varying way. Another approach we can look at is to actually use measurements and have a measurement-based feedback control. So we can consider measurements on this system. The simplest case you might consider are so-called projective measurements, where each quantum state is projected onto corresponding eigenspace of the measurement operator every time a measurement is made, and then that can be used as part of a measurement feedback-based control system. So we adjust the control input then on the basis of measurements. Okay, so that area of open loop control using the Schrodinger picture is quite an interesting area, but I haven't done that much research in that area, and the sort of research that I've more concentrated on is in the Heisenberg picture, and in particular with these QSDE models. quantum stochastic differential equations, and in particular, in terms of systems which have a particular kind of QSDE model, which is a linear QSDE. So in these QSDE models, the variables are actually observables, which are operators on the underlying Hilbert space, which is an infinite dimensional Hilbert space. And so sort of following the standard practice in classical control, we can write down a set of linear quantum stochastic differential equations in this vector matrix form, where X is a vector of system observables, U is a vector of quantum linear processes, which are like quantum noise acting on the system, and Y represents the output of the system, which might correspond to an output measurement. So this corresponds to an open quantum system because the system is interacting with the environment. We might have quantum noise acting on the system, but the difference between a classical system, which could look very similar in terms of the equations, is that the elements of these quantities X, Y, and U are actually operators rather than just real quantities. And so because they're operators, they don't necessarily commute with each other. So it's kind of like a non-commutative version of classical linear systems theory. So we will study quite a lot this idea of quantum linear systems, and in particular, quantum linear system is can be thought of as a collection of quantum harmonic oscillators, where we might have n of these quantum harmonic oscillators, and they're driven by inputs which are bosonic fields, like say optical fields or microwave fields. So we might have n oscillators within our quantum system interacting with m fields. So one way of describing the dynamics of such a linear quantum system is in terms of the annihilation and creation operators for the underlying quantum harmonic oscillators. So we usually use these notation A, bold A, for annihilation operator, and its adjoint as an operator is called the creation operator. So case could be thought of as an operator corresponding to the creation of a photon and the annihilation of a photon. And these are operators on an underlying infinite dimensional Hilbert space. And because they're operators, they don't, as I say, necessarily commute. And so, in fact, what we get is the following standard canonical commutation relationships. So the first one says that the annihilation operator for any two annihilation operators actually do commute with each other, and any two creation operators actually commute with each other. And if we have the annihilation and creation operator for different systems, they also commute with each other. For different harmonic oscillators, they commute with each other. But if they are the annihilation and creation operator for the same harmonic oscillator, then the commutator is not 0, but 1. Here we've sort of normalized Planck's constant to 1, so the commutator becomes 1, and so they no longer commute. So in this linear case, we have the dynamics of the system described by a Hamiltonian, and we can write this Hamiltonian in a particular form, which is this quadratic form. So here, again, the Hamiltonian is an operator on the underlying system, on the underlying Hilbert space, and it's made up of a quadratic form of these annihilation and creation operators. So it's convenient to collect all these annihilation operators into a vector. It's like the vector of annihilation operators. Then we also get the vector of creation operators by taking the adjoints. And then we can stack those two things together in a vector with both the annihilation and creation operators, and the Hamiltonian will be a quadratic form in terms of all those operators. And here, omega is just a given Hermitian matrix which defines which actual Hamiltonian we have. So that's kind of the first part, describing the dynamics of our linear quantum system, and it describes the internal dynamics, but also we've got our system interacting with these fields. And so the way we describe that is another operator called the coupling operator. So this operator describes how each of the harmonic oscillators interact with the fields. And in this linear case, that will be a linear combination of these underlying annihilation creation operators. So essentially, we've just got two complex matrices, C minus and C plus, that tells us what that linear combination is. So the fields which interact with our system are also described by annihilation and creation operators. They're on their own Hilbert space, which is called a Fock space, which is a special kind of a Hilbert space. And we can describe equations which relate those operators to the underlying dynamics. So in particular, if we've got the Hamiltonian matrix and the coupling operator matrices, we can write down these linear QSDEs for any given linear quantum system in a form like this, the same form as we had before, but now the variables are these annihilation and creation operators, and the matrices A, B, C, and D are complex matrices that define our dynamics. So the variables are these operators on an underlying Hilbert space, but the dynamics are defined by these finite matrices, finite dimensional matrices, which are complex matrices. And by analyzing the dynamics of such a system, then we can find formulas for these matrices in this QSDE description in terms of the underlying Hamiltonian, which is defined by the matrix omega, the underlying coupling operator, which is defined by the matrices C minus and C plus. And there's also a matrix J here, which occurs quite a lot in these kind of equations. It's just a diagonal matrix of an identity and minus the identity. And we've also used some notation here, which is commonly used about how we calculate the different matrices. I won't go into that. So this is a complex annihilation and creation representation of a linear quantum system. So often what we want to do is apply methods of classical control theory to problems in quantum control. And it turns out that models like this look very much like the models that occur in classical control theory, but there is one difference in that in a quantum system model like this, these matrices are complex matrices, whereas in classical control theory, those matrices would be real matrices. Now, it turns out that we can do a change of variables to rewrite this model in terms of real matrices rather than complex matrices. And in this case, we're essentially changing the underlying variables. So far we've talked about the underlying variables being these annihilation and creation operators, but an equivalent way is to represent the underlying variables in terms of what are called position and momentum operators. And it turns out that these are self-adjoint operators, which will in the end mean that the corresponding dynamics will be in terms of real matrices A, B, C, and D. So there's a simple transformation that we can apply to our annihilation creation operators to get the position and momentum operators, both for the internal dynamics of the system and also for the input U, which corresponds to the input field, and for the output Y, which corresponds to the output field. So in this case, the components of this are the individual position and momentum operators for each quantum harmonic oscillator, which are what's called conjugate variables, because also they don't commute. In fact, these variables have their own commutation relationships, which are very similar to the ones we had before. If you've got different harmonic oscillators, J and K are not the same, then all these terms are zero. But if they're the same, and we look at the commutator between the position and momentum for the same oscillator, then we get an answer which is non-zero, i.e. they don't commute. Okay, so the next thing I'll look at is continuing on this study of these quantum linear systems is what kind of control systems we might apply to them and how we might extend ideas from classical control theory to quantum control theory. And one of the first things we looked at was a notion of H-infinity control, which goes back quite a long way in the control theory literature. Really, it's about trying to design feedback controllers to make the closed loop system attenuate disturbances that we want to get rid of, and also to be robust against uncertainty. So I'm not going to go into the details about why this particular idea will do these things, but the disturbance attenuation actually idea should be reasonably easy to see. So we start with a plant or a system to be controlled, which has one of these QSDE models in terms of annihilation, in terms of position and momentum operators. So that means that all of these matrices are real matrices. And the reason why we've got a lot of terms here is we've got our input fields, which we divide up into a number of different types. And in particular, we've got these two types, V and W, which represent disturbances, and this type, which represents control input. So in looking at the two disturbances, we're going to think of V as just representing the quantum noise, which we can't really do anything about, and W, which represents an external disturbance, which we are trying to attenuate via the use of control. So in terms of the outputs, we've got an output Z, which represents the variable for which we're trying to attenuate the disturbance W. So we want to try and reduce the effect of W on Z. That's sort of the standard H-infinity problem. And the way we do that is we want to design a feedback control system where we measure this output Y, put it through some kind of controller, and feed that back into our control input U. So that would be a measurement feedback controller and control system. And if we do that in such a way to reduce the effect of this disturbance W on the output Z, well, then that would be an H-infinity controller. So the sort of controller we're looking at is actually, in this case, a classical system, because we're assuming we can measure that output Y, we feed it through a classical system, and then produce an output U, which is also a classical output, which then goes into our quantum plant. So the controller has these variables, which actually, in this measurement feedback case, are classical quantities, just real numbers, which evolve with time. But later on, we'll talk about the coherent case when this system is also a quantum system. So this idea of attenuating the disturbances is related to a notion in control theory called the strictly bounded real property with disturbance attenuation. So the idea is that if we if we attenuate the disturbances by a factor of G, then then that's equivalent to the existence of some energy function V such that this energy function has this relationship. And so that means that this quantity here is what's called the supply rate, which is kind of, we're attenuating the disturbance by an amount G. And so if we do that, then the overall energy will go down modulo some linear increase here due to the additional quantum noise that we have. So the way we can solve this problem of designing such a controller turns out to be very similar to the corresponding H-infinity problem that occurred in classical control theory. And there was some assumptions about the dynamics that was used in classical theory, and the way that we synthesize the control law is the same as in the classical theory. It's solving some matrix equations. All these matrices here are known except for this matrix X, which is unknown. This equation is called the Riccardi equation. There's a standard numerical way of solving this. And similarly, we've got another such Riccardi equation where the unknown matrix is Y. Everything else here is known. We can solve those equations. And then if we get solutions which satisfy some assumptions, they have to be what's called stabilizing solutions. That means this matrix has all of its eigenvalues in the left half of the complex plane. Then also the size of both matrices multiplied together has to be smaller than 1 in terms of spectral radius. Then that will give us a controller which solves this H-infinity problem in that attenuates these disturbances by the factor G. And not only and in fact, we've got a formula for the matrices in the controller. So this is a synthesis procedure which tells us how we can construct that classical controller. So this is actually quite an old result where we proved this result that if we can find these solutions to the Riccardi equations, then we can solve the problem with this controller. And furthermore, that if any such controller exists which solves the problem, then our method will work. So it's actually a necessary, close to being a necessary and sufficient condition. So let's give an example from quantum optics about how this approach works. So let's suppose our plant is an optical cavity. It's just a single mode with a single annihilation operator A, but it's coupled to 3 optical channels. There's 3 mirrors in the cavity, and they're coupled to 3 fields. There's like an input and output field for each channel, which are labeled V, W, and U, which in this example are going to have the same form, the same meanings as we had in the original model. So U is going to be our control, which for which we have the feedback control to produce U. W is the disturbance that we're trying to attenuate, and V is additional quantum noise, which we can't do anything about. And we want to design our control system so that the influence of W on this output Z, which is that output channel coming out of that mirror there, is attenuated by some given amount. So we suppose that Y is the quadrature, the real quadrature of this output field, which we can measure in practice using a homodynamic detection measurement. The input field, the input is a coherent state, which we can achieve by modulating a laser which is producing this input field. So to apply this H-infinity method, we would then first of all write down a model of the plant. So we've got the various input fields, the 2 different output fields we're concerned with, and the corresponding dynamics. So it's the form of a problem we looked at before, where we've defined where we get all these matrices. They're all just 2x2 matrices, or 2x1 matrices, 1x2, 2x1 in some cases. Then we're going to choose this attenuation factor to be this value, 0.667, so 2/3. So we're going to try and attenuate that signal by a factor of 2/3. And then we see if we can do it by trying to solve those Riccardi equations. We do, in fact, find solutions to those Riccardi equations, and it turns out they satisfy all our assumptions. So that means we can solve the problem. Then we can construct the matrices in the controller, and this controller is a classical controller, so it's just be implemented in a classical way, such as with electronics, and then it would be applied to our quantum plant like this. So that was our plant. This was our output. We're measuring that. So we go through the homodyne detector to obtain the measured signal Y. Then we go through this classical device where we've designed the dynamics of that. That produces our signal here, which then modulates a laser. So, and that produces the optical signal, which is the input to our quantum system. And the way we've designed it, it means that the effect of this disturbance on W on the output Z is attenuated by a factor of 0.667. Okay, so that's one way we've looked at linear quantum control, and in particular, this H-infinity approach to linear quantum control. So the next thing we want to consider is, suppose that rather than having this quantum measurement and this modulator and doing things classically, we want to do everything optically. So there's a sort of general idea that we expect this should be better, because making measurements of a quantum system, we're losing quantum information. So things, we've lost some information there, so maybe we can't do things as well. So the next thing to do is see if we can do this in an entirely quantum way, the so-called coherent feedback control. Now, a fundamental issue when doing this is that not all the QSDEs that we've looked at would actually correspond to physical quantum systems satisfying the laws of quantum mechanics. And so when we synthesize our controller, we want to make sure that we actually do get a controller which would correspond to a physical quantum system, and that means it satisfies this property of physical realizability. And so, say we're solving this H-infinity problem, then we want to make sure that when we get our controller, it has this physical realizability property. There's another related classical problem called the LQG problem, linear quadratic Gaussian optimal control problem, which also we might want to solve using a coherent controller. So in fact, that's what we'll look at now. So again, let's suppose we've got our quantum plant in this real form in terms of annihilation creation operators. We've got a control input field and a quantum noise input field. We've got an output field, which we can't really call a measurement output, because we're now not intending to do actually any measurements. We just want to connect this measurement output to another quantum system, which is the controller, which is then connected to the control input. So we've also got this quantum noise, which is acting on our system. We've got our control input, and we want to have a controller that controls this thing, which we want to be a physical quantum system. So let's suppose we're going to have a quantum controller which has a form like this. It might look very complicated, but we had to have a number of additional inputs and a number of additional outputs to make sure that we can meet all the requirements of physical realizability. So some of these are not actually used in the control process, they're just like additional noise. But the idea is that the input to our controller is the output for the plant, this Y, and the output to the controller is the input to the plant is the output to the controller, this U. And so we've got more quantum noises in our controller, so we have this physical realizability property. So this is a block diagram of what we're proposing. Start off with the plant. It's got some noise, it's got a control input, it's got a Z, which we'll talk about later in terms of the performance of our control system. It's got an output which is not measured, but just feeds into the controller, which produces the input U. And the controller also has some of its own noises and then some unused outputs. So then we get a closed loop system by combining all these dynamics of both the plant and the controller, and it's described by some combined dynamics like this. And then we introduce a cost function because we want to solve an optimal control problem. So we want to find the controller which minimizes some cost. And that cost is this average quantum, the quantum expectation of this output Z, and then averaging that over time, integrating it over time and averaging that. So our output Z is really just used in saying, what do we want to minimize in designing our feedback control system? And that's the quantum LQG problem, and the fact that our controller has to be quantum makes it our coherent quantum LQG problem. So the solution to this problem means that we have to have a controller which is physically realizable. So what we want is a controller that is physically realizable. We want the closed loop system to be stable. So this closed loop matrix here describing the dynamics has to have all of its eigenvalues, which are in the left half of the complex plane. That's called Hurwitz. And then the closed loop cost function should be minimized. And the way we can calculate this closed loop cost function is by solving a matrix equation like this, which is called the Arpanoff equation. And here the matrix P is the unknown variable, it's the solution to this Arpanoff equation. And then we can evaluate the cost function according to this formula. So the physical realizability of our controller, it turns out, can be represented in terms of a bunch of constraints on the controller matrices. And so these kind of look quite complicated, but, and I guess to some extent they are, but at least then we've got a mathematical description of our coherent quantum control problem is we want to minimize the cost subject to the, we minimize the cost with respect to the variables in the controller and also subject to the physical realizability constraints and the dynamics of the plant. So it turns out because of these constraints are quite complicated and they're non-convex constraints, that this quantum LQG control problem turns out to be actually a very difficult one to solve. So the problem was first formulated in this paper in 2009, and there was an attempt to find a numerical solution to it. It turned out that numerical solution was not really that practical. It was hugely computationally demanding and only really ever worked for the case when we had a single mode. So just a single quantum harmonic oscillator, then we managed to solve the problem. But for any other examples, we could never find a solution. Okay, so what I want to talk about now is some subsequent work after that, where rather than trying to find these optimal solutions to the coherent LQG problem, we were looking for some suboptimal solution, maybe not quite as good as being optimal, but still pretty good. So the idea here was that we just forget about this physical realizability constraint for a while and then solve the classical LQG problem and then see if we can modify our controller to make it physically realizable. So the idea was if we had any potential controller, which had some model like this. Then we add noises to that to make it something like this, which was physically realizable. So we start off with this AC, BC, and CC. That's how we designed our controller, ignoring physical realizability. And then we choose these additional matrices to make the overall thing physically realizable, which amounts to adding extra quantum noises to the controller. And what we want to do is do that in a way that adds the minimum amount of additional quantum noises. So the way we did that was, in fact, just to minimize the dimension of this vector. So you've got the actual output, which we have to have, and then these additional quantum noises, sorry, that's the actual input, which we have to add to make it physically realizable. We don't want to add any more than we need to. So the approach taken was to modify our LQG problem by adding an extra term to the cost function. And so the idea of this adding this extra term to the cost function was that when we convert our controller from just a classical controller to a physically realizable one, we're going to add some extra noise. So in a heuristic sense, we could maybe take that into account by adding an extra term in our cost function, which somehow would take that into account. And so this row here in this extra term is some free parameter. So we do that, we've got a new cost function, then we solve the LQG problem without regard to physically realizable. And it turns out that problem can be solved as well using these Riccardi equation methods, and it's straightforward to solve. Then we make our controller, which is not physically realizable by adding these extra noises. Then we evaluate the closed loop cost, and then we repeat this process as we adjust this extra parameter row until we minimize the closed loop cost. So it's not going to give us the exact optimum, but it's going to give us something that's close. So let's apply this to an example. And this example is an optical cavity. It's got two mirrors. The input is some thermal noise. It's got some thermal noise coming in over here. And we want to add to that a coherent controller, which is over here, taking the light coming out of this mirror, going through some optical system, and then feeding it back in. So if we didn't do anything, if we just left off that system, then we'll get a certain level of our cost function, and then we want to see if we can improve on that by adding the controller. So, and we also compare it with the case when we use measurement, where, as I said before, we could use a detector, in this case a heterodyne detector, and just a standard classical LQG controller. So our cost function here is going to be just the expected number of photons in the cavity. So our aim is to make the expected number of photons very small, so cool down the cavity via the use of this controller. And we're going to do this depending on how much classical thermal noise we have. This parameter Kn determines how much classical noise we've got. So we applied our algorithm, and we've looked at three possible cases as a function of the thermal noise strength. So on the y-axis, we've got our expected photon number. So the smaller it is, the cooler we've made it. And on the x-axis is the strength of the thermal noise. So, and then we've got three lines here. The blue line is if we do nothing. We just have no controller. So as we add less thermal noise, then it's going to get cooler. So that's this straight line. And if we get down to very, very small thermal noises, it turns out the controller is not really doing much. We can't get much advantage without a significant amount of thermal noise. And the next case is where we use the measurement-based control. That's the green line here. And we actually get some significant improvement around this region here. And then the final case is the red case with the coherent controller using our algorithm. And it's, again, a bit of an improvement over the measurement case, which is what we expected, because doing measurements, we're losing quantum information, whereas if we do everything coherently, we should be able to get some advantage. So as I said, in the limit, when we've got no thermal noise, then the system only has this vacuum noise, the so-called quantum noise, and the controller really can't do anything better than not doing anything at all. But if there is thermal noise there, then the controller can be effective. So the last thing I want to talk about is another area in this quantum linear systems theory, which is the so-called quantum Kalman decomposition. And the Kalman decomposition is a very well-known way of analyzing linear systems, not linear quantum systems in the classical world, but it turns out it can be applied in the quantum world as well. And it's useful in that it can be helpful in understanding how we can make measurements on quantum systems without suffering the effects of back action. So the main result is that says for any one of these linear quantum systems that we've been talking about, we can do a change of variables which transforms to the system which has this very particular form. So we're assuming we're in the position and momentum framework, so all these matrices are real, and then we get this very particular form which might look complicated here, but if we look at a block diagram corresponding to what this means, it means that the system is broken up into a number of subsystems. And the first subsystem is this one here, which is in control theory terms called controllable and observable. That means it's connected to the input U, which is like, say, the noise input, and it's also connected to the output Y, which maybe is how we measure it. So that one is kind of like a normal quantum system. And then the other extreme down the bottom here is this one, not controllable, not observable, and that means that there's actually no path from the input noise to that system, so it's unaffected by noise, but also it doesn't affect the output at all. There's no path from here to the output, so it's just sort of sitting there, but it's invisible to the outside world. But the interesting other parts are these two parts here, controllable and observable, and not controllable, controllable and not observable, and not controllable and observable. And it turns out in the quantum world, these things are actually conjugate to each other. They have to be of the same dimension, and they have some useful properties in terms of back action free measurement. So to see this, let's look at an example, which is an optomechanical system which has actually been implemented experimentally using superconducting microwave circuits. This experimental system, what they did, they weren't aware of our results, but our results just provide a way of analyzing what they achieved in this experiment. So there's an optical cavity here, which is actually at microwave frequency, so a microwave cavity, and then two mechanical oscillators, which are at a macro scale. They're actually MEMS type scale oscillators. So this result was reported in Nature, and the result they achieved was entanglement between the two macroscopic mechanical oscillators achieved by using the optical coupling between the two oscillators via the optical cavity. So to apply our approach to it, we need to write down the QSTE models. First of all, we write down the Hamiltonian in terms of the modes, the three modes here, one for each mechanical oscillator and one for the optical cavity. So we've got A1, A2, A3 and their conjugates. We've also got coupling to the outside world, we're assuming the only coupling to the outside world is via the optical cavity. So we get this coupling operator, and then in terms of this Kalman decomposition, we have the following variables. So that leads us to a system which has this particular form, which is this Kalman decomposition form. And if we look at the block diagram here, then these are the various blocks that we've got. And in particular, we've got this block here, which affects the output, which is going to be measured, but is not affected by the noise. So we can effectively get some sort of noise-free or back-action-free measurement of this block here. So all the back action from the noise goes into its complex conjugate, so into its conjugate variables. So this is like the momentum variables, the conjugate of that are the position variables. It gets all the back action, but we can do this back action free measurement of these variables here. And so that was kind of the entire idea of this paper, which appeared in Nature, was to be able to do this back action free measurement and then be able to measure without having the back action effects, the entanglement property between the two oscillators. So by using this Kalman decomposition, we can kind of understand why that happened. So to conclude, I've just covered a few of the areas of quantum control engineering. It's a really broad area. What I've talked about is just a few different areas that I've worked on, and there's many more different areas that can be talked about in this whole area of quantum control engineering. The approaches I talked about were based on the sort of approaches that I've looked at, and in particular, these approaches have involved starting with classical feedback control ideas and trying to extend those to quantum problems. And of course, there's lots of other approaches, but I think that's where I'll stop. Okay, thank you.
Thanks a lot, Ian. So any questions from the audience for Ian?
May I ask a question?
Yeah.
Okay. Well, for control, of course, you need measurements, and you mentioned that.
Well, I guess what I was saying is in some cases you need measurements, but sometimes we can do things without measurements, whereby we simply couple the controller to the plant. So I think I didn't explain it here, but a very simple case in the classical world is, for example, a door closer, where you attach a mechanical device to your door to stop it slamming shut. So you can think of it as a feedback system where it kind of measures it doesn't measure, but it couples to the door system and somehow changes its dynamics. So that's this idea of coherent control, where we couple some dynamics to some controller dynamics to some plant dynamics to change the overall behavior. So I wouldn't necessarily call it measurement, but because measurement has a particular meaning, as we said, in quantum mechanics. And sometimes we do use measurement, but sometimes we want to avoid that, because in quantum mechanics, measurements destroys information, which means we might not be able to do things as well.
So that brings me to the next question, actually, that when quantum feedback controller is also a quantum system, it is called quantum control. That's what it divides. So if you make a strong measurement on a quantum system, it collapses into one of the states, right? Up to states.
Yeah, that's right. If you do a
classical then.
Yeah.
So you cannot make a quantum control out of that, right?
Well, you can make a quantum controller that's measurement based, but that has a detrimental effect on the system. In the extreme case, it's this quantum collapse. But you can do weak quantum measurements. So if you don't directly measurement, then in the Schrodinger picture, you think of it as collapsing the quantum state or changing the quantum state. In the Heisenberg picture, you think of adding noise onto the system, so adding quantum noise. But they're both different ways of saying the same thing. which is disturbing the system by doing a classical measurement. And so in the last section, I talked about back action, which is like another way of thinking about this effect, where if you do a measurement, you have this back action effect, which is the Heisenberg picture, thinking of how you're adding noise into the system by disturbing it, by measuring it. And you can still do things in a way that the back action only affects some variables, but not necessarily the ones you're interested in.
Okay, so for weak measurements, I understand that it doesn't destroy the quantum system.
Yeah.
So you can generate the quantum control, right?
Yeah.
But for strong measurements, you won't be able to generate that, I guess.
Well, it will have a very strong disturbing effect on it. So you might not be able to achieve what you want to achieve by using such strong measurements. So it still may be possible depending on what you're doing. And as I say, this kind of way of thinking is normally in the Schrodinger picture. And so there are quite a lot of feedback results around in the Schrodinger picture as well, where people are using strong measurements, maybe periodically measuring the state, which does cause the quantum collapse, but it still might be possible to achieve what you want to achieve. You still may be able to steer the state to where you want to go, even though you're collapsing the state at each step. So it's not necessarily so that it's impossible to control a quantum system using a very strong measurement. It just depends how you do it and what you want to achieve.
Okay. So I have another question, that the last example that you have given with the superconducting system,
Yeah,
that's a mechanical oscillators. Are they simply the membranes vibrating?
yes, yeah. So these are two vibrating membranes. Both membranes are coupled to the microwave cavity, and that's the only way that the two membranes are coupled together is via this microwave cavity.
Mm-hmm. So the noise part and the control part, I haven't understood for this.
Well, so this was an experiment that really wasn't done on the basis of looking at the control part. So the idea of the experiment was to be able to do this in such a way that you got a entanglement between the two mechanical cavities, but also that you could verify that entanglement by measuring the optical cavity. And so to be able to verify that the entanglement occurred, then they needed to be able to avoid the effect of this back action. So when they did the measurement, if the back action was disturbing the system too much, then they could never verify that it was there was entanglement between the two kind of hidden mechanical parts. But by carefully designing the experiment, they were able to avoid that. And so what my analysis here was showing was just you can think about that in a control systems way, in terms of thinking about the entanglement that they're interested in is actually represented in terms of this subsystem here, which we can measure because the subsystem affects this system. It will still have this noise, this quantum noise here, but there's not the back action noise actually goes into the other subsystem. So that meant that that the level of the noise was small enough so that they could actually verify that entanglement was occurring. So it's really just a way of thinking about the results that they had.
Okay, thank you.
All right. Any other questions from anybody else in the audience? So Ian, I had a question actually. You showed in towards the beginning, the matrices A, K, B, and C. Those are the ones that we intend to design for the controller, right? So
let's see. So
yeah.
So say in this one.
Oh, yeah, right.
Yes, so say in this H infinity problem, we start off with all these matrices in the plant. So in control systems, you have these notions of a plant, the thing you start off with, and then the controller, which is the thing you design. So that controller could either be some classical system involving some measurements, or it could be some quantum system just involving some interconnections.
Right. So I had another question. So I remember having worked on something called coherent classical estimation, right? So where
Yes, that's
you're
right.
talking about a hybrid controller. So, so how does that compare to some of the things that you have shown? Like, just generally asking, because having a classical part within the controller, wouldn't it be like a useful thing to have?
Yeah, I guess I never talked about that, but yeah, you could have a situation where the controller has both a quantum part and a classical part, and then maybe that would be an advantage. And I guess in the problem that you looked at, we weren't actually trying to control something, we're actually trying to measure something. So we couldn't have something which was completely coherent, because we wanted to get some classical quantity out. We wanted to be able to get some measurement out. So, but we thought that you could maybe do better if you had some purely classical estimation scheme where everything happened in the classical world. Maybe you couldn't do as well as if you had some part of the estimation scheme in the classical world and some part in the quantum world. So it's kind of an extension of these ideas, recognizing that there may not, in some cases, there may not be a clear demarcation between measurement-based and coherent, that you might have a hybrid between some coherent parts and some measurement-based parts.
Right. And also, I think as far as controlling a quantum system is concerned, I mean, it's actually more difficult to control, like it's more difficult to control a quantum system compared to a classical system, right? So in some sense,
well, yeah, in terms, so I mean, there's lots of different issues there by what you mean by more difficult. I mean, one thing is that the mathematics tends to be more difficult because we've got these extra constraints, these physical realizability constraints, so that it's mathematically more difficult. Another thing is maybe the performance you can achieve is worse because we've got these constraints that come from quantum mechanics. Things like Heisenberg's uncertainty principle says that you can't kind of make a control system perfectly good. That there's a limit to how good you can do, you can do these things because of the underlying quantum mechanics. So it's kind of it's more difficult in two ways. One, in terms of how we design our controllers, and two, in terms of what we can achieve.
Yeah, the reason why I was asking this question is because if you have a hybrid controller and you optimize only part of only the classical part, the parameters of the classical part of the controller, and you don't touch the quantum part at all, would it not give a very good control scheme? And it's generally because we are actually doing something similar in the machine learning where it's called reservoir computing. You know, the quantum reservoir is actually untouched.
Yeah, but yeah, I mean, that's probably a sort of a reasonable suboptimal approach. And maybe it's a little bit related to the sort of suboptimal approach I talked about.
Okay.
Where, yeah, where the sort of overall optimum is maybe too hard to achieve. But if we just kind of treat parts of the problem as classical, then maybe we can do almost as good as if we could if we find the overall optimum, but it's much easier mathematically to find.
Okay, yeah. So anybody else has any other question for Professor Petersen? Professor Das, are you there?
Yes, I'm here. I mean, I think I really enjoyed the talk. Thank you very much, Professor Petersen.
Yeah. So Ian, Professor Das is actually our center director.
Okay. Hello.
Yeah. Yeah. All right. So if there are no other questions, so Professor Das, you want to say something?
Well, again, I would like to thank you, Professor Petersen, for a really very enlightening talk. I mean, I think my colleagues enjoyed it as well.
Okay, thank you. Yeah, thanks. It was my pleasure.
Thank you.
All right. Thanks, Ian, and thanks everyone for joining. We hope we have more talks from Professor Petersen in the future. Thanks a lot.
Okay, thanks everyone for listening.
Thank you. Thank you.
Thank you so much. Goodbye.
Bye.